So now that we talked about why Gossett invented his T distribution, I want to talk to you a little bit about what it looks like and what it's trying to do for us. So hopefully my last lecture made the point that we can no longer use the Z distribution when deciding our rejection regions if we don't know the population standard deviation. And I hope you also understand it's very unlikely for us to have the population standard deviation. It should feel weird that I have been saying, well, we just know that the mu is this and the sigma is that. But who just goes around knowing population parameters? So it's more often the case that we don't just know these things, but instead we have samples and we use those samples to tell us a little bit about the population from which they came. So Z distributions are actually rarely used because we don't often look at population data. We're looking at little baby samples. The only people I've seen use Z distributions are sociologists. Sometimes they will measure entire populations because they look at death records or birth records. Or if it's not the entire population, it's pretty darn close. But other than that, very rarely do we see Z distribution research published. We usually see people doing T distributions. So how do they differ, the T and the Z? How much the T distribution differs from the normal Z distribution depends on the sample size. So the T distribution differs from that normal curve when the sample size is small, because the estimate of the population variance is based on a small sample. So if we look at this picture, the solid line is the normal Z distribution. And the T distribution, as the sample size goes down, we kind of push the T distribution down. And again, remember, it's like a ball of clay. So I've smushed it down. If I smush it down, then we'll see it kind of float out into the tails. You can see how this dotted line doesn't really look like a normal distribution because it has this little bump in the tails. It still has the same mass, but if I'm pushing the distribution down, then that mass has to go out into the tails. So what we know is that the T distribution, it gets shorter and wider as the sample size gets smaller. If you have a small sample size, you're going to have a short distribution that's very wide. But if you add to your sample size, the more people you add, the more it pulls in, and then it ends up being taller, so much that at some point, your T distribution will start to look just like the solid line Z distribution because you've measured so many people, it's approximated the population. So what I would like you to take away from this slide is that the T distribution for small sample sizes is smushed down, so it's not as tall, and it's pushed out into the tails. And so if it's pushed out into the tails, let's look at this picture here. You can see that if this is 2.5% of the upper part of the Z distribution, do you see how this hump in the T distribution would make up more mass? So 2.5% would be closer to over here in the T distribution. So if you use 1.96 as a cutoff for the upper 2.5%, you should see that the T distribution, that's actually much larger area than 2.5%. It may be closer to 5%. And so since that's so much mass, then what we would see is that using the typical 1.96 and negative 1.96 cutoffs would be giving us larger rejection regions than is really fair. So we have to decide and look at the table that Gossett made and said, okay, what is the cutoff now for the upper 2.5%? Here's the trick though. This changes shape for every different sample size. So it's going to get shorter and wider for small sample sizes, and then as you get more and more people in your study, it's going to move inward more and more and get taller more and more and more, and so it starts to look like the Z distribution. So that means that Gossett would actually have to make a table with a page for every possible sample size. So if you think about the Z table that I gave you, remember I had the areas under the curve for every Z score. We would have to have that for every T score, but a new page for every possible sample size because the shape of the distribution changes for each sample size. if you recall, when we moved into inferential statistics, we were only really interested in the 2.5% area and the 5% area, right? So we did the two-tailed rejection regions or the one-tailed rejection regions. So now we know that when we look at our T distribution, we only really need to assess the 2.5% in the upper tail and lower tail, and the 5% in the upper tail or lower tail, and that's really all that we need. And so the T table I'm going to share with you today is really only identifying those two areas. It's not every area under the T distribution. It's only if the C column were at 2.5% or at 5%. And then we've managed to list every possible sample size on one page. And so we're going to take another video to learn how to read the T table. But before we do that, I do want to highlight the formula that is used for the T distribution. So if you remember the Z distribution, when we had a sample Z, it was your sample mean minus the mu divided by our known population standard deviation divided by the square root of our sample size. So our T formula is very similar. It is saying take the mean of our sample minus our mu divided by the standard deviation of the sample divided by the square root of our sample size. So the only difference really is two things. First, we set this one equal to Z, whereas now we're going to set it equal to T to remind ourselves to look at the T distribution rejection region. And on this one, we would look at the Z distribution rejection region. And then the Z is where we know the population standard deviation. The T is what we use when we don't know the population standard deviation. So we're going to use the standard deviation we got from our baby sample. And so we are going to use that in the formula. So they work very much the same way, except this one doesn't require that we just happen to know the standard deviation of the population. We are going to use what we have at our fingertips, which is the sample. Okay, so check into the next video to learn about how to read the table so we can find our new rejection regions.